In section 9.4, we talk about ionic bonding and its relationship to lattice energy. Now, when you form an ionic compound, and you can look at this formation in terms of a lot of different directions, we're finding that this process is typically exothermic. Now, we have a lot of terms here in this chapter especially that, since we skipped ahead a little bit in the book and we didn't cover some of the earlier chapters about thermodynamics and chemistry yet, we're going to go back to those. That's how our sequence works. That they're using a couple of words here and there that are not probably familiar to you. So exothermic, exo means exit, thermic means heat energy, so we'll just look at this as energy. So this means that exothermic means heat energy leaves the system, the compound that we're interested in. So if this is happening, if a process is exothermic, it means that energy inside that system is coming out, and if it happens from the formation of an ionic compound, then that energy has to be coming from somewhere. So where does the energy that's released when an ionic compound come from? Well, you could think that maybe it's due to the electron transfer, that maybe that results in a more stable compound, and with more stability in the compound, meaning the extra energy that was there originally that made it less stable has to be given off and gotten rid of. But that's actually a very small component. What we actually see is most of this energy is coming from the formation of the ionic matrix itself. Okay, so what do I mean by an ionic matrix? Well, if I have sodium ions and chlorine ions, they're going to form ionic bonds by the nature of the charges being attracted. But this negative portion over here on the chlorine is just going to attract another sodium ion, which will in turn attract another chlorine ion. And you can imagine this in 2 dimensions, and you can imagine this in 3 dimensions, and that's the crystal and the lattice work that results from these ions getting together and forming a compound. Now, what we see as our chemical formula for ionic compounds is the simplest whole number ratio of the different elements present in them. But in reality, those are not discrete units of sodium and chloride together. They're actually these large extended crystalline networks. And when this forms, if we remember the equation that describes charge and attraction to charge, due to charge, we have that force being proportional to charges involved over the square of the radius between them. As these 2 positive and negative charged components come together, this force of attraction is different because we are putting these closer together instead of farther apart. So that energy that was required to get them farther apart is now released as they come closer together again. You can kind of think of this proportionally to if I have a brick at the bottom of a base of a building, and then I lift that brick up and put it at the top of the building. It now has a certain amount of energy because it's separated from what it's attracted to, which is gravity pulling it towards the ground. If I kick this brick off, it goes back down. It's going to have to release that energy somehow, usually by kinetic energy going into the sidewalk, noise being let off, a little bit of heat, whatever it's releasing it as. But energy is given off as it converts its potential energy from its location into the new location where it no longer has that potential energy. So this charge separated has energy. The charge when the compound forms being together means it has to release that excess energy that's no longer there from the charges being separate. So what do we do with this? Well, we can look at the bond strength in an ionic bond by looking at the energy change of the formation of a compound of that particular substance as it forms from its elements in their natural states. So solid sodium and diatomic chlorine gas combine in a 1 to 1.5 ratio to form sodium chloride solid. And we can look at this as delta H. Now what does delta H means? Delta H means change in enthalpy. And what is enthalpy? It's kind of complicated, but what we can think of it as, in chemistry terms, is just a simple way, at least for now, as the energy in chemical bonds. Okay? So this amount of energy can be calculated because we can see exactly how much energy is given off or taken in. In this case, if the whole enthalpy, meaning bond energy, of the system, meaning the components, the sodium, the chloride, if that decreases, that means energy is given off. So where does that energy have to go that's being lost as this compound forms? Means it's given off. And we can measure that. Well, we can also measure, kind of in a stepwise process, all of the steps that would have to go into turning solid sodium and half a molecule of chlorine gas into sodium chloride ions that are now solid and together. And we can do that to try and get to this overall idea of lattice energy, which is the energy of the bonds made up in this little three-dimensional crystal. That's not this one. That's not the formation enthalpy. That's the amount of energy given off by the forming of these bonds. But it's not necessarily this lattice energy, which represents the energy in the bonds. Because there's more than that than goes into it. So we can look at these different steps. So we can say, all right, I start with solid sodium and gas molecules of chlorine. Step one, perhaps we say that we're going to turn the sodium into a gas by heating it. And that heating it takes a certain amount of energy to overcome the bonds that make this a solid. So we have to put energy in to the ingredients, which means that the energy of the ingredients increases. And you can kind of agree that a gas molecule will have more energy in it than a solid molecule. That's why it moves around and that's why it's a gas. Well, then maybe we're saying we're going to form chlorine atoms from the chlorine molecule. So we call this then the energy associated with dissociation, dissociating one chlorine from another. So that's going to require some energy because we have to overcome the energy in the bonds, slice those in half. So that requires putting energy in as well. So energy goes in, added from the outside through heat or some other means, and that means the energy of the system increases again. Now we have gas atoms of sodium and gas atoms of chlorine. We're going to have to ionize the sodium, meaning we're going to have to take an electron away from it so that it becomes sodium gas. And that, sodium gas ions specifically, and that's going to require its own amount of energy input that's going to change the bond energy of the system again. Because now I've taken the electron away, the electron wants to go back, so having it away has sent a portion of potential energy that goes into that particular ingredient. Now we're going to add an electron to chlorine, so we're going to put that in there because it has a certain amount of affinity, and that's the type of energy that we refer to this as, is the electron affinity energy of chlorine atoms, and make this chlorine ion. Now that is a process that's actually energetically favorable. That chlorine really wants that so it can become like a noble gas and have a much more stable arrangement. So if the system loses energy then because it's in a more stable environment, it does that by releasing the energy of that it had by having that separation from the stable noble gas state. And now finally, with the positive sodium ions in gas state and the negative chloride ions in gas state, the two will come together, they'll condense from a gas, form a solid crystal of sodium chloride solid, and that's the definition of the lattice energy, the energy change from gas ions to solid uh, combined crystal, and that's representing that energy within the bonds of that ionic substance. You're probably thinking, yeah, what am I supposed to do with all this? Well, all of this adds up. So we can look at all of these different steps, like step 1. We can go to a table. We can say, all right, step 1, the amount of energy it takes to go from solid directly to gas. And they call that the energy of sublimation. And there are tables for this. And we look at the value, and we see that for each sodium mole of sodium that does this, we need about 108 kilojoules, and joules being the unit of energy. And then we look at the amount of energy in the bond of chlorine atoms. So we're going to split this apart, this dissociation. And this is about 244 kilojoules, but we only have half of a molecule, so we need about 122 kilojoules of energy. And that's for breaking the chlorine bond. And the sublimation was to go from a solid sodium to a gas sodium. So then 3, I ionize the sodium, ionization. So we can look that up on a chart and see that that takes about 496 kilojoules worth of energy. And what that is that's taking a sodium, that's a gas, and turning it into a sodium plus ion, plus getting rid of that electron. And then that's the step here. And then finally the electron affinity is a step where we get energy back from it, where we take a chlorine atom, add an electron, and get chloride gas ions, and we get back, so we're going to say negative 349 kilojoules worth of energy. All right, so this last step, we don't know. That's the lattice energy. We don't necessarily know what that is. We don't have a table directly for that. But we can calculate it knowing all of these things plus this formation energy. This is something we can look up based off of a number of tables of bonds and different other things. And we can see that this particular energy and that's sodium solid plus half a chlorine molecule gas going to solid sodium chloride. That is going to be exothermic, meaning giving off energy to the tune of about 411 kilojoules. Okay. So all of these energies have to add up to this one. So this 108, and then we go up by another 100, this one right here, 108, and go up by another 122, and go up by 496, and then go back down a little bit by about 349, and then how much must this be if this space here is negative 411? Okay, so we're going to calculate that all out. And when we do that, and we set up the equation, we're saying negative 411 kilojoules is equal to 108 kilojoules plus 122 kilojoules plus 496 kilojoules, we're just adding these all up, plus a negative 349 kilojoules, plus the lattice energy. Energy of the lattice. So we solve all this, and what we get is that the lattice energy, punch all this through the calculator, and we get negative 788 kilojoules, meaning it's giving off 788 kilojoules worth of energy, so that must be the energy within the bonds present there. Okay, excellent.